Good morning, Michael.
Morning.
Good morning, guys. Apologies for being a little late.
Good morning, Alan.
You're actually right on time.
Hello. Right. Sorry, I didn't realize the time and I carried away with something else. Right. I also noticed that this meeting clashes with the monthly server meeting, but I'll skip that one. That's not too much of a problem. Right, today is the 28th. Me, Peter, and Michael. All right. Give it a couple more minutes, see if we see anyone else.
I have a couple of questions for you, Alan.
Yeah.
Who did all of those great drawings? Is it SolidWorks, and did you do it?
I did most of it initially, and it's not SolidWorks, although it's a product called Shaper 3D.
Okay.
On the Macs, it works on the Macs, the iPads, and on PCs, but we can export in step format and the rest. And actually, my son helped out with some of the extra details, like on the what's it called? Jesus. The water manifold.
Okay.
All the details in that, he actually did that.
Well, I think your collection totally is impressive.
Thank you. I appreciate it.
My second question is, are you lined up to propose to the various organizations that are connected to the CHIPS Act?
I'm only lined up at the moment for this one we're all sort of trying to work on. The Oak Ridge National Labs New Frontiers RFP, which as we said was on hold at the moment. But that should be freed up eventually. I don't think it's going to be cancelled. It's just somebody mentioned it was continuing resolution issues.
So what's it called? The Oak Ridge National Labs?
Yeah, New Frontiers.
New Frontiers.
So the RFP is, we've shared it. I thought I sent it to you. I can send it to you again if you like.
Okay.
There's a draft that's been out since last year in October-ish, I guess. And we were told that the final draft would be anywhere from at the beginning of this year. But then I just got an email a couple of weeks ago saying that it was on hold for the moment.
So do you have any idea about the dollars that could be available and the number of people competing for those dollars?
Yes and no. Well, yes, I do. Well, so first of all, the response that needs to go in is they told me would be 4 to 6 weeks in the final release of the final RFP.
Okay,
So the clock ticks rapidly then. In terms of the funding, they said that they had an allocation of, I believe it was 23 million.
okay,
And they said they didn't know, they had an expectation that they would fund multiple people, but they didn't know how many. Multiple companies or multiple bids. And they said the 23 million may change. I guess if they get quality proposals, and I believe that they are funded from the CHIPS Act money. So
I see.
so it sounds like if they get quality proposals and they like what they see, then they might be able to find some more money.
Yeah. Oh, that's encouraging.
Yeah, and I mean, for ourselves, I don't have any. I mean, I think we can probably get away with more than 1 million, but probably less than 5 million for what we're going to do here. That's just my gut feel. But
Yeah,
at the end of the day, I didn't want to restrict any of the contributors to say, well, I need this much and I need that much. If we could get numbers in the, if we could get what we're going to do written down in the proposal, and we can get companies that are contributing to that and want to work together, what the effort's going to be from each of them and what the dollars and cents are from each of them, then
yes,
then we'll roll it up and see what our number is. If it ends up being 100 million, then we might have a problem. But
right.
so
That sounds good. Yeah.
so that's where we're at there. There are other things going on. There is the Army labs as well. I can't remember the name, but ARNL had something. Army Research National Labs. I'm not, again, don't quote me on that. But there are some other proposals that are out there. There's obviously other things we can go for. But this one is the one that they had an RFI out in 22, which we submitted, and it's on our wiki, is what we submitted in 2022. I can even flash that up, but that one, we sent the response in, we presented to them, we had a feedback session with them, and the current RFP that's in draft form, you can see some of our inputs seem to be reflected in there, like our community effort, this systems approach through OCP. They're a bit fed up with the round robbing of these machines of, it's AMD's turn, it's Intel's turn, or through HPE. And the reality is the vendors are down to just one, being HPE now. And that's not an ideal scenario. They're also fed up with, they want more modularity in the machines, so more upgradability, serviceability. And they're not getting, with the round robin machines, they have to rip and replace. And on the system management side, which is not to do with this work stream, but the system management side, they have to start from scratch every time because it's a different software from each of the vendors.
Yeah. So seems like you've been learning from their challenges and responding. So this is good.
Yeah, but I mean the problem we've got is they have this one throat to choke mentality for good reason. And so the round robin affair with one big contractor and then a few subs does seem to keep them happy. And to say the least, we're going to be a bit like a bunch of small companies. It's going to be like herding cats. And so we do, so that we could do with a systems integrator overall. We've got one name in the frame. I've been talking to some others. The ex-CTO of NASA, Bob Ciotti, he's just retired from NASA, still plugged into them, but he's working for a value-added reseller that works closely with the government already in terms of putting machines in and having IT people and on site, etc., supporting those machines. And so I'm hoping that I can put him together with the other company, which is another startup trying to get their own funding, that is proposing that they can be the system integrator. So we've got that idea at the top, that top level, and then we've got these sections underneath being the power and thermal, the system management, and the universal interconnector, the free or the interconnect side of things, are the three big subcategories. And then we've got the category of we need to build real modules. And
So that's it. Sorry.
Yeah, go on.
The Secretary of Commerce is her name is something like Germondo. But anyway, she gave a talk about the CHIPS funding just a couple of days ago.
Okay.
And one thing that I picked up on was that it is their intention to fund some small companies.
Right. Okay. No, that's good. Well, so so when we were in, I was in consultation with them on how they wanted a proposal from us, because they said, look, we're working across the silos here. There's a ton of stuff. It's a radical approach, but there's nuggets in all of it. Like I said, we could just build a power thermal and mechanical test vehicle with like load slammers and loads, and not put anybody's expensive chips in there. We just make sure, because it's fundamentally the core of our design is fundamentally a power and thermal re-architecture. So we could do a separate bid for just the power and thermal test vehicle to say this is a new structure for building these types of machines. And that could be funded standalone. Similarly, the system management side of things, the HPC system management is notoriously been, like I say, incompatible. There's a lot of open source in the BMC side, etc., and making all of that a properly open source. So that would be another pocket, which we got a separate section on. Including from a security perspective, we've got this this root of trust in everything being open source, so you can actually see all of the code that's in a particular design. Is quite important for these security people. And then finally, this interconnect is we're trying to get to this co-packaged optics world, but we're in this copper world, and is there a more of a graceful transition from passive copper, active optical, near packaged optics, and then co-packaged optics? And could we make more of one sort of try and design an interconnect to cover all the bases and all of this proliferation of protocols? So that's the so those are the big three areas that I personally feel each of them could get their own funding if they put a separate application in. And but obviously the idea would we take all of those and we put it together under a holistic POC, is where the system integrator would come in above it with a specific module. And the target application area that I've come down to is ASIC emulation with FPGAs, which is something I did in my previous company that I founded, Nowtech, back in the mid-90s. We actually fell into the ASIC emulation business in the late 90s, early 2000s, where it was 25% of our revenue. And what we didn't realize, we didn't even know where it was coming from. And our competition in those days was two companies called Aptix and QuickTurn. And they were massively expensive machines for ASIC emulation. And people wanted to do it on the cheap. Now, our cards were expensive because FPGAs were expensive, but we were considerably cheaper than these Aptix boxes and QuickTurn. Well, it turns out with this chiplet enablement that's going on as well, if you're familiar with that, I've proposed in the OCP chiplet community that we could do with some sort of organic growth approach for chiplet development, and an ASIC emulation platform where you could replace FPGA emulation with real chiplets as they arrive, sort of integrate them is I call it hardware in the loop. You add a piece of real hardware as it becomes available, a real chiplet, but you plug it into the rest of the emulation platform to see that it still works as the previous emulation did, that your real chiplet conforms to the emulation previously, would be a good way to, and so if we built an emulation platform based on this, we could actually, that might be a good use case. I've had a couple of people interested in that. And in fact, a company I'm working with has the emulation platforms today are basically owned by Synopsys and Mentor, and I guess Cadence. They have their own. And I get the impression they have these big machines stuffed full of FPGAs, and they lease them out with their simulations. You know, when you're simulating one of their IP cores or your design, they lease these out. Well, I'm talking to companies that are saying, sod that for a game of soldiers, it's too expensive. And they're even building their own emulation platforms. So I was thinking, well, if so all we need to do, and because I'm an FPGA pioneer in FPGA computing, I've got all the relationships with the FPGA houses, Xilinx in particular, and I've already got access to all the chip information on their big ASIC chip. And so I was thinking that could be our first HPCM module that we would build, and we could start that, and then we've got a target application that we can actually get going sooner than later.
How much power do these FPGAs need?
Well, you were reading my mind, Michael. So I'm getting a bit more pragmatic as well on this. I've been talking to Rise. I've been talking to a few people about pulling a vacuum, including ChatGPT, about the difficulties. PSI wise, it doesn't seem that difficult. It's like one bar is 14 PSI. I've learned, and you were saying, Peter, that we need to pull about a quarter of a bar, I guess, or about 0.4 of a bar to boil at 65C, or somebody told me that. And it was you, yeah, it was you, Peter. And so the actual differential pressure that we need to pull is about 8 PSI or something like that. Don't quote me on the numbers. But you know, on that front, I thought, now, whereas Boyd were saying if we pressurize it, they wanted to pressurize it at 40 PSI. And I'm going, well, 8 PSI, putting a vacuum of 8 PSI ought to be a lot easier than forcing a pressure of 40 PSI, but I get the impression that is actually not the case. So
well, from a mechanical perspective.
Yeah, from a pump perspective.
No. From your module perspective, the 40 PSI positive is going to try to blow the module apart.
It can, yeah, and a vacuum sucks it together, which is a benefit, I'm assuming.
Yes.
So Alan,
yeah, go on.
I'd like to give you the 2 data points for the vacuum versus boiling temperature. So at 0.4 of an atmosphere, the boiling point is 76 degrees C. And at
0.4 is 76.
And at 0.2, it's 60.
0.4 is 76. We see. And 0.2 is 60.
Yes.
So 0.25 is the 0.65 is going to be in the region of 0.2, a quarter of a bar then.
That's right.
Okay, yeah. So pulling a quarter of a bar. So yeah, so mechanically pulling that vacuum, I don't know. So I'm talking to people. Nobody really knows, except for I just get the feedback that pulling a vacuum is harder than pressurizing. Now, not in terms of containing it, in terms of the mechanical pumping of it. And again, that doesn't make sense to me. So, but I'm no expert in that area. I don't know if you guys have any views on that.
So I did some exploration along these lines using Gemini, which is the outgrowth of Bard by Google, and it's a ChatGPT competitor. And I found Gemini to be very useful.
Okay.
And my conclusion was that to pull a vacuum is about 20 times harder than doing single phase water cooling. So there's
Oh, 20 times harder than single phase, not than pressurizing.
right, and it's partly due to the fact that the pumps have trouble. Then I have to work with vapor as well as with water, and the community appears to be very nervous about doing this. They say another problem is leaks. You know, you build your system and then they leak. So that's just a couple of issues. So it's bad news for you, but I'm my input is that it's very difficult to do vacuum.
I would also think that all the commercial parts like valves and pumps and seals and QDCs and everything like that are all designed for pressurized systems.
Yeah,
So
I
if
think
you
that's
put
right.
if you went below atmospheric, all the seals are pointed in the wrong directions and they're
Yes. I actually asked ChatGPT, why is it harder to pull a vacuum than make a pressure? And it gave me all these reasons as to why. And I thought, oh yeah, that one makes sense. And then I asked it the same question again. I said, why is it harder to pressurize an external pressurization rather than pulling a vacuum? You know, I asked the question the other way around, and it gave me a list of reasons. So, but the interesting thing was on that sealing thing, I realized that obviously if you put your seals, just like you said, Michael, in one way, then pressurizing will force the extra sealing, whereas you put them the other way, then vacuum will force extra sealing. Now it's interesting that our design as it stands is attractive to vacuum pulling because it seals more. So anyway, but yeah, that's a good point. Yeah, so it's
now air conditioning systems typically work just like this though.
They do they?
Well, they're partially liquid,
Vacuum.
partially vapor.
Yes, of course. They put in a vacuum. They are converting to from liquid to vapor, aren't they? That's what they do.
And it's not until after the compressor that it's really fully liquid.
Yeah, so the compressor cools it all down and turns it into a liquid, puts it into your HVAC system. Is that right?
So actually, it's the condenser that cools the hot vapor, and you'll get a mixture of cooled vapor and some liquid on that. And once that goes through the compressor and comes out the other side, you should have cooled liquid.
Right. So you have cooled liquid, then you cool the house, and then that
Well,
turns back into a vapor again.
So that goes into an evaporator.
Yeah.
Which it's just a radiator. And there's an expansion valve at the inlet to the radiator that allows some of the liquid to spray into the low pressure side of that and absorbs the energy.
Right.
So instead of having an evaporator on there, you could have your compute module.
Right. Exactly. And the thing is interesting as well, Peter. I was thinking we're not like an HVAC system, I guess, where you're literally returning gas. You know, everything's boiled off and it's 100% gas. We're going to be passing the water over this, and yes, the chip area is going to be boiling, but there's going to be quite a, relatively speaking, a volume of water around there that's not getting up to that temperature and it's flowing through, right? So that once it leaves the chip surface, it'll be, you know, so what you want to do is if we're pulling the flow so that the temperature is whatever we want for energy reuse. Let's say we're pulling an energy reuse temperature of 65. Then if we set the boiling temperature to 66, if I got my numbers the right way around, then it will boil, but it will liquefy again when it mixes with the rest of the water that's still liquid, and it will eject as liquid in the end, or it might have bubbles in it. But as it returns back up to the pump and back up to the heat exchanger, it'll already be a liquid again. anyway. So it's not as though am I making any sense on that, or doesn't that add up?
I don't think it gets to be liquid until the condenser.
No, in our design I'm on about, because we don't have, when you say,
Well, if you're going for heat reuse, it's whatever is going to, the condenser, chiller, heat exchanger, whatever you've got that's going to reduce the temperature. You need to get it back
right,
below the boiling point of the water at whatever pressure you've got.
So we've got, yeah. So in the design, right, if you guys both remember the basic design that I had, is we've got this one column per set of modules. We've got 8 modules in a column. And we'd have a valve on every module, an adjustable valve on every module that would close. Depend on the power being consumed by the module, the valve would close until the flow rate was slow enough so the ejected water would be at our desired reuse temperature, 65°C. Right, so you'd have a temperature sensor on the ejection of the module saying the water is 65°C. And if it's less than 65°C, it closes the valve a bit more. If it's more than 65°C, it opens the valve a little bit more on every module, right? And that is now that temperature is then dependent on how much power we're burning in the entire module, the media and the big chip. So if we've got this little control loop controlling this little valve, saying the temperature is coming out at 65, happy days, then if the so assuming we're boiling at some point with this, so actually let's wind back a bit. If we're only burning 200 watts and not a kilowatt in the processor at this particular moment in time, it'll stay liquid, and we're trying to return 65°C, or would it? Yeah, depending on what we set the boiling. Well, actually, so the vacuum will vary, one would assume, depending on how much we open and close this valve, right? This valve will control this vacuum. And if we really close the valve so it's almost closed, so the vacuum we're pulling with the pump happens to be this 1/4 of a bar, then it starts to boil like crazy. But if we set that boiling point, then that boiling point varies depending on the valve position.
Well, I would hope that the vacuum would be relatively constant.
Well, so you'd set a vacuum of some sort in the main vertical loop, and then each module would be affected by that, by the additional valve on each module. And this is where
your flow valve there is going to work just like the evaporation valve that's in an air conditioning system. So everything that's on the other side of the valve will be lower pressure.
Yes.
Yeah, so you'd be pulling vacuum inside of the module and on the return side of the coolant.
Yes.
So that would keep the boiling point relatively low.
Yes.
And as you opened the valve to let more coolant in, because you've got more power consumption, then you'd get potentially more boiling, and you'd have to be conscious of maintaining the vacuum and the return side of the cooling system.
Right.
So the vacuum pumps may have to work harder.
So you would need
you would
need to. I guess your pumps would be needing to do a certain level of work. That's where I don't understand how you pull that back. We need an expansion chamber, I guess. It is to be able to pull that vacuum to store the excess.
But you still need a loop that's going to measure the vacuum and control the speed of the vacuum pump.
So, right. Michael, anywhere in the loop, does it get exposed to atmosphere ambient?
Exposed, I would say no. Now, one of the problems I think you're going to probably end up with water vapor going through the vacuum pump, and I'm not sure how they're going to like that. And
They
that's
don't
also going
like
to,
that. Yeah, they
yeah,
don't
that's
like that.
also going to cause a coolant loss.
So that water vapor going through the vacuum pump. So on the return path, you've got all the channels coming in, and so you've got temperature controlling the valves locally on each of the modules. So all of the water coming out is a given 65 degrees C, let's say, for sake of argument.
And what's the boiling point?
Well, the boiling point will depend on the vacuum we pulled. So
Right.
if
So
we're not pulling a vacuum, so the thing is, well, so that's a good point. All right, thank you. Yes. So the other thing temperature we're measuring is we're measuring the temperature of the chip, right?
So you really want to, the whole idea is to manage die temperatures.
No, exactly. Right. On the same page.
But you've got a subsidiary thing there where you're trying to keep the coolant warm enough so that you can do heat reuse.
Right. So the idea is that's the entire goal of this is that we have a consistent output temperature for reuse purposes. So that is our design point, is this is a reuse job.
But an overriding goal on that would be keeping the die temperatures below cooking or below throttling.
So die temperatures, I don't know how much you know about the die temperatures, but forever commercial die temperatures have been about 85 C. More recently, they've upped it to about 105 C, but I still use 85. If you're IBM System Z mainframe, they don't like their die to go above 65 C.
Yeah, but Intel's won't throttle until 105, 120, depending on which CPU you've got.
Right, so it's 105 seems to be the one that everyone's relaxed the 85 up to. But let's just use 85. I mean, I'd like to go with 85 if we could.
Well, you've got so many chips, keeping your MTBF reasonable by keeping the temperature down would also be another good goal.
Exactly. Right. And so let's just say 85. So we got a 20 degree C differential. So basically, this is a good discussion.
This is where you start needing the whiteboard and sketch this stuff out, because you've got thermal losses between the die and the packaging and
it's
whatever
the thermal resistance to the water. So to Peter's point is if we can make it boil, it's a 7 times improvement in energy, the thermal transfer. Is that right, Peter?
Let me say it again. So the joules of energy to evaporate water is 7 times as large as the joules of energy to heat that same quantity of water between 0 and 100 C.
Right.
But like you said, pulling a vacuum on it, you could make that threshold 65 degrees C.
Right.
By the way, the 7 times number gets smaller as you go to a vacuum, but that's a secondary point.
But still, it's a large change between just liquid cooling and vapor and two-phase cooling.
Yes, that's right.
So I got it right. So if we need 65 C water out, and we're fundamentally controlling this valve for 65 degrees C water out, right? So this is adding an additional local vacuum beyond the vacuum of the entire loop that's being poured by the pumps. Basically, we're monitoring our die temperature, and as long as our die temperature is the thermal resistance from the die to the water needs to be no more than 20 degrees C, 20 degrees C for the wattage being burnt. So as long as we've got a design, so if that, let's just say that 20 degrees C, if we're sitting at 65 degrees C ambient, which is our water ambient, right? So if we're sitting at 65 degrees C ambient and this 20 degrees C delta, if the actual water flowing directly over this conformally coated copper die that we're talking about, with Nanan in that, and Peter, if that transfer through a single layer of copper on this thing to the water is more than 20 degrees C, which will be depending on the power being burnt by that processor, then
you need a higher coolant flow rate.
You need a higher coolant flow rate. And well, not a higher coolant flow rate. You would if you stay liquid.
Yes.
But
if you're manipulating the boiling point, you could at low power consumptions, you could have a completely liquid system, because you don't need the additional cooling capacity that you'd get by going two-phase.
Right. So
now you start
working against each other, aren't they? Because if you pull a vacuum, you're going to be reducing the flow rate.
Yes, and you might not maintain your 65 degrees C.
That's.
So you've got multiple
well, hang on. So hang on. So what we're saying then, I don't actually, to be honest, I personally, it doesn't matter if you've got more than 65C. It's just don't be less than 65C. So what you're saying if we've got the efficiency of water transferring heat from the die to the water, which is liquid, we need more flow to keep it cool.
You've also got something else in there to manage, which is the total coolant flow rate that you need for your heat reuse. If you were running at 25% maximum power and you needed very, very little coolant and you had it under a vacuum, so you were running in two-phase, your coolant flow rate could be very, very small because your cooling system's very efficient. And is that enough coolant flow rate to keep your downstream customer happy?
Yeah, that's a good point. That's a very good point. I haven't thought of that.
So if you pulled a vacuum on it to manipulate the boiling point and had very little coolant flow rate, very efficient cooling, you'd have very little coolant downstream, even though it might be at 65C.
So we've got on every vertical column of modules, of 8 modules, we've got a heat exchanger that heat exchanges with the facility water. So ideally you would like that 100% transfer of the 65C into the facility water, but like you say, you're
going to lose some.
You're going to lose some, but you need to also, obviously, if you're the flow rate of the facility water and the different powers of each column of modules would have to aggregate to, yeah, I see.
Well, if the machine isn't consuming much power and your facility coolant flow rate is high, you're not going to contribute much to heating the facility water.
Facility water. No, you're going to have to control the facility water as well, right? You're going to have a separate loop on the control loop on the facility water as well in terms of flow rates, just like we have the modules.
So do you really want to? Well, this is something that needs to be part of the cooling management, the software that's managing the whole system.
No, it'll be so it looks like we've got 3 layers of control going on in the cooling.
But in the long run, are you really trying to manage this when the machine is busy so that it's at near maximum energy consumption?
Obviously we want to get to a point where the design point means if every module is consuming its rated, its maximum rated power, that yes, you can still cool it, right? But obviously on the assumption, probably if you got max design point, max TDP or whatever you want to call it, then if it's operating most of the time at 50% TDP, then you're slowing everything down, right? Flow rates and all that.
I'd like to ask a very basic question. Supposing we have a closed loop system and the chamber where your electronics is, let's say it's at 0.2 atmosphere. Now, as Michael pointed out, the outlet and the cooling at the outlet needs to also be at 0.2 atmosphere. Otherwise, you won't be able to move the water out. So my question is, who gets it to 0.2 atmospheres? Because, you know, normally a pump operates and it increases the pressure, right?
Right.
So I see a vacuum pump and a coolant pump. So you've got a
So,
coolant circulating pump, and you've got some other pump in there that's going to pull a vacuum on the coolant chamber.
Right.
So you're going to have an accumulator someplace.
It's an expansion chamber. Yes, you've got two
Yeah.
pumps either side of an expansion chamber. So the one pulling the vacuum can fill the expansion chamber, and the coolant can make sure the flow rate stays the same coming out of it.
Right.
okay.
But the challenge I see in that is that the expansion chamber would probably be on the hot side.
Yes.
Because you need something to separate the vapor from the liquid, so that you get mostly liquid into the pump, because the bubbles in the pump will cause cavitation, and it's really, really tough on the impellers.
Right.
So you need, like an expansion chamber or something that's also got a chiller of some kind in it, so that it would take the water vapor that's in there and turn it back to straight water. And
So hang on a minute. What about if on the vertical column, if we've got the hot return coming up the pipe, it actually goes through so if it goes through the heat exchanger, then you're saying the bubbles through the heat exchanger are going to kill the heat exchanger. Is that what you're saying?
no, not the heat exchanger won't bother it. The
Okay,
pump
all
is
right,
the
so
thing.
let me continue then. So if we've got the 65 seawater coming out of all the modules coming up the return pipe, and it first goes through the heat exchanger to the facility water, then it will come out of the heat exchanger colder and as purely as a liquid, and the bubbles will hopefully have been gone. And then we've got the vacuum pump pulling the vacuum that then goes into the expansion chamber, or whatever else you called it.
Well, you'd probably have the pump connected to the expansion chamber.
Right. Okay. The pump on the expansion chamber, and then the other coolant pump would be after that. So
Right.
so all of the pumps would be on the return side after the heat exchange.
So between the accumulator tank, if the pump is directly connected to the accumulator tank, on the outlet side of the pump all the way up to the coolant flow valve could be above atmospheric.
Say that again, I missed that.
So you've got liquid water in the bottom of the expansion tank. The expansion tank itself is below atmospheric.
Right.
But now the pump is pushing against the coolant flow valve that's at your module. So the line between the pump and your coolant flow valve could be well above atmospheric, but it doesn't really make any difference to the way this is going to work.
But if that were true, Michael, you wouldn't get the flow, because if you're going from low pressure to high pressure, the water won't flow.
Yeah, no, it's going to be high. You're actually the expansion chamber. What do you call the expansion chamber? That expansion chamber will be higher than atmospheric pressure, because you're pulling a vacuum from the modules, so therefore you're forcing extra pressure into the expansion.
Well, it depends on where the coolant pump is.
Like you say, we need a whiteboard.
Is the coolant pump? Yeah, where in the loop is the coolant pump?
I was assuming the coolant pump was after the expansion chamber, or whatever you call it.
Right. Okay. So the expansion chamber is below atmospheric.
Yes.
Okay.
So the only thing that's going to change the coolant pressure to anything below atmospheric is going to be the coolant pump itself. So now you have a throttling valve that's at your module that's restricting the flow of the coolant, and you have a pump that's pushing against the throttling valve. So that small section between the coolant circulation pump and the throttling valves and the modules could be above atmospheric, but that has nothing to do with the behavior of the coolant. Because as soon as the coolant gets on the other side of the coolant flow valve, the throttling valve in there, it goes below atmospheric.
Right. I know the throttling valves are on every module. That's what you mean by throttling valve, yeah.
Yep. This is looking very like an air conditioning system.
Well, I guess that's exactly what it is, really.
Because this is exactly how the expansion valve in a air conditioner in your house or your car works.
Yeah. Or on your hot
It,
water as well, you have the expansion valve to stop the banging of the pipes when you turn the taps on.
Michael, do you know what kind of pump can be a vacuum pump?
Google vacuum pumps, you'll find millions of them.
Because you know, centrifugal pump, I don't think it qualifies.
No, they're probably roots or something like. If there's a style of blower that was used on diesel engines and things like that, that's called a roots blower.
Okay. All right, I'll look it up.
And they're relatively
Pretty sizable.
well, they can be all over the map. They could be up to thousands of horsepower. And so we would need a relatively small one, I would think.
So is there a simulator for this stuff? Is there a software simulator for designing these pumping systems?
I have no idea.
Yeah, it feels like a filter design, electrical design that we're doing here. I get a simulation on it. Interesting. Well, it's a good conversation, guys. Thank you. It's
yeah, this is something that you could probably do a little PowerPoint slide that would show the circulation loop and where the
I guess this is what we could get into this proposal is if we can sort of describe on paper roughly what it is and say
it needs development work.
This is the idea and we just need to develop and prove it, right? So that's I mean, I think it'd be worth I mean, if the other thing we need to do that I'm still a little bit is Boyder talking about this pressurized approach as opposed to a vacuum approach. And whenever we talk about this conformal coating, people are saying there's not enough surface area between the copper and the water and the fluid to do the heat transfer effectively. So you need these veins, or you need to, I guess it's this pressurized spraying that what Boyd's talking about. But if we could get some numbers behind if we use water instead of dielectric, it's this much better. If we boil it at low temperature, it's this 7 times better than that. And this is the sort of the sketch of the design that we think we could build to make this, to test this concept out.
But you can also use two-phase with the dielectric.
You can do two-phase with the dielectric as well. And then, and as the ad said, actually, if you do two-phase with the dielectric, I presume
then you probably don't need a vacuum pump.
Why would that? Oh, because you can get a dielectric that boils at a lower temperature.
Right.
The trouble with the dielectric is it's very unpopular, right? From an environment.
And it's really expensive.
So making it happen would.
And the energy is way less than water.
Yeah, so it's terrible at the heat transfer, right, compared to water.
Yeah.
So
even a two-phase?
Yes. Two-phase dielectric is way less effective than two-phase water.
Huh.
Is it because of the starting point? Is it still 7 times better than the dielectric by itself in liquid, or is it even a smaller ratio, Peter?
I think it's basic that the heat of vaporization is a lot less in the dielectric.
I mean, so if we can do this in a vacuum, we can pour the water down. We got the. I mean, so the entire point of the OCP HPC is redefining computer architecture from the ground up for sustainability and energy-centric computing. That's my sort of vision of this or mission.
So if you could get two-phase water to work, that would make all the greenies really happy. It would make the bean counters happy, and it would be
cost-wise. And
it would be interesting technology.
It could end up being a lot. I mean, all it is saying nobody's bothered trying to pull a vacuum before, I guess, is the bottom line on this. And it does, from this conversation, if it is simply an HVAC, you know, it reminds, I don't know if you guys know about Tesla's Octavalve in their car and the EV. But
I've read a little bit about it.
It's an 8-way heat exchanger. So all of the heat generation and cooling and whatever you need, basically they stuck it all in the one pump, whereas it's like 7 or 8, it's 8 pumps in a traditional ICE car. You know, you need to cool the battery, you need to warm the cabin, or sometimes you need to cool the cabin, and so you
warm the battery.
You've got various loops, or warm the battery. Yeah, you've got various loops going on, and they basically designed it all into this one. They call it Octavalve pump. And Musk was saying actually we might get into the HVAC business. But by the way, actually to extend this for you both, because we're talking HVAC, the whole idea of this was we got this module, right, that we can put 50,000 of them in 50,000 of them in a data center for a frontier supercomputer or the likes. But that doesn't stop us from putting 20 of these modules in a telecom box on the side of the street for an edge application.
And if it's lower TDP, then you could just keep it liquid water and not worry about two-phase.
Or even if it's the high TDP, you know, you need 10 GPUs in the corner instead of 50,000 of them or whatever. You know, you can still put serious compute in the side of the road. And you've got the water, and if you've got a heat network, like in my hometown in Bristol, UK, they've got something called the Bristol Heat Network. You can feed the water into that Bristol Heat Network, right? So the hot water. So you know, you start to do some planning with the cities, etc. But then the final one is you can go to offices. You can put it in the office. You know, so you have a wall in the office where it's built in all of the heating and ventilation systems there. That this plumbing is plumbed into the hot water system and is plumbed into the heating system, and it's plumbed into the air conditioning if necessary. So all of that is in one design of the building, with the compute now as a utility piece. The wall is the same in everybody's home. And then we come to our own individual houses. And what really struck me just literally less than 6 months ago, I was around a friend of mine's house where his son's a teenager. He's just been working a part-time job, saved up $3,000 and built himself a serious gaming PC. It burns 800 watts, and his room is like a freaking oven, right? So they got to turn the air conditioning on of the whole house just to heat his room, or put a special one in his room. It's like, well, if when you built a house, you had 4 module sites or whatever built in and plumbed into the hot water system in the HVAC system, then you go and buy your gaming PC as a module, and you just plug it in this wall, and it doesn't heat the room up, and it all gets managed by the home heating network. So it works across. So this HVAC thinking that you're bringing in here is pretty damned applicable to all of this anyway.
Yeah, we're researching geothermal heating and cooling for our house.
Well, there you go. Right, there's that as well, right? So you can bring
during the summer you get free hot water.
Yeah,
because they take the energy from the HVAC system and dump it into the hot water storage tank, and then any excess goes out, in our case, out into the dirt.
So what we're doing is we're bringing the compute piece of this into this bigger equation.
Well, I've got some machines at home that consume upwards of 8,000 watts. I could connect them. I've got one disk drive that needs 2,000 watts.
Holy shit! Really? A disk drive?
Yeah, it's 56 years old.
Holy shit! 2K disk drive. No thanks.
for
Okay.
170 megabytes. So something like that, if you had geothermal in your house, the geo side of it, the dirt or the pump side of it is just like what you've got for your city.
Right.
Gentlemen, I have to take off now.
All right, Peter.
Okay.
Coming.
Bye.
Yep.
Yeah. So Michael,
This is interesting tech, and
well, yeah.
it would be nice to get some federal funding to do the research and do the prototypes to see if you can make this work. And the architecture that you're talking about by doing this in small loops takes away the scale up problem.
Yes. Yeah. Because each one just feeds in, eight modules feed into the infrastructure network.
So the scale up is liquid water, not two-phase water.
Yes.
So that means there's not much to learn on that, and you've got these relatively small manageable loops on there. And
That's the interesting question. Relatively
right,
small manageable loops.
right,
These when I was at OCP, whenever I look at these things, like I go to the Boyd stand and I see these ginormous boxes saying, "Oh, we're cooling 80 kilowatts in this box or whatever," and it's
Yep.
like, and you got the size of these bloody pumps and all this, and I'm thinking, so okay, we got 2 kilowatts per module, so we got 16, call it 20 kilowatts per column. And I've got little tiny pumps and modules.
Yeah.
These pipes, and I'm thinking my pipes might be the diameter of these pipes, the flow of the water. But if we're pulling a vacuum and we're actually reducing flow, that's the other thing is, can you keep flow up while you pull a vacuum? You need to pull a you need to have a good set of pumps to continue to pull the vacuum and pull a serious flow.
Yeah, the only thing that worries me a little bit about this is all of the two-phase systems that I've seen have something for a condenser in them to take the vapor and turn it back to a liquid. At some of the shows that I've been to, they have a thing that looks like an aquarium with a bunch of server boards in it.
Yes.
And the water circulate. I mean, sorry, coolant circulation in it, and you get bubbles coming out of the top of the tank, which is the two-phase vapor. Right. And they have something at the top of it to cool it and drop it back into the tank as a cooled liquid. Works like a charm. This is going to be a little bit more challenging. Because
well, your heat exchanger, don't forget that ours is going to be the heat exchanger with the facility water. So you can buy off of you can buy this little tiny 15 kilowatt. What's the name of the company? They're 100 years old. But you've got these heat exchangers. They're like little plates, very thin plates, and you put the water in and it goes through these plates and it comes out and it exchanges with the facility water. So
a lot of the ones that we use
isn't it?
A lot of the ones that we use can be like a copper plate with pipes brazed onto both sides of the plate.
Right.
So it looks like
it. That's it.
Yeah.
So and do they just stack them like a stack of cards?
Yeah.
They go in and out.
We use them up to a megawatt.
Right. So these things I got this physical size of them from the OCP Regional Summit last year. They said this thing can do 15 kilowatts, and it's no much bigger than what I'm showing here in my hands.
The 100 kilowatt ones that we use are 0.5 meter cubic.
Right. So that sounds about right.
So they're not big.
So would we need an expansion chamber if we can do it there? You don't need, because your bubbles are going to get condensed in that heat exchanger and be liquid coming out. So you don't need an expansion chamber.
I think you're going to, because you've got to have some place for the to get the bubbles out of the water, and
before the heat exchanger,
before the pump. before the circulator pump.
Well, I'm thinking, would the heat exchanger not actually end up condensing it so there are no bubbles left before they get to the pump, assuming the pump is after the heat exchanger?
I think that's a research question.
Right. Okay.
You know, I think that I really don't know. Has anybody done this before, or?
Well, that's the beauty. This is what I love about this is you get all the, so Boyd's saying we got pressurized to 40 psi, and then hearing the NAD and Peter talking about putting a vacuum in conformal coating, it all gets really pretty damned exciting to me. And I'm thinking, yeah, okay, no, but we've never done it that way, so therefore nobody's bloody interested, right? And now we're the three of us just having a short conversation and saying, okay, maybe it is doable. The only thing in
So
my head right now is that the pumps are going to be fucking ginormous to pull this vacuum, you know, versus
I
doing
don't
a
think
little
so.
thing like this.
I'm not convinced of that.
Right. Well,
So,
I mean, that's my biggest concern is I've
so,
got lovely
so
model.
if we try to visualize this whole thing, so right at the throttling valve or expansion valve, whatever you want to call it, that's in there on the coolant pump side of that, you've got a relatively low temperature solid liquid, just like an air conditioning system. And once that starts allowing coolant to flow into your heat exchanger chamber, you're going to, depending on how much energy you're dumping into the coolant at that point, you're going to potentially boil the coolant. And that was the whole idea. So the whole idea that I see out of the two-phase water is the heat exchange between the coolant and the the chips, more or less. So you've got to have something that's going to conduct the energy from the chips into the coolant. And if you're just using a liquid coolant of any kind, the transfer of energy from your fins, more or less, into the coolant isn't terribly efficient.
Right.
So
This is where you need to increase the surface area of the copper for touching the water.
Right. So you would end up, and the pressure for a single phase, I think, is an issue of flow rate, not of heat exchange or anything like that. So you would, if you tried to design the module, you'd say, okay, I've got a TDP of 400 watts or something like that. What's my energy absorption capability of my coolant? How big does the heat exchanger, the fins and stuff like that, need to be in order to be able to dump 400 watts into the coolant with a temperature rise of no more than 20 degrees? And you would end up with some pretty substantial contact surface area between your fins and your coolant in order to be able to dump that energy into the coolant. So my understanding is the idea of the two-phase coolant is that it would reduce the amount of contact surface that you need between the fins and the coolant.
Yes, yes, completely agree.
Because it's much more efficient transfer of energy on there. So
that's the idea. The perfect scenario is a conformal coating of copper on top of the piece of silicon that you're cooling, just the area of that silicon. You can cool that 1 kilowatt or so just with boiling water.
Because you're doing two-phase.
And you get, whereas you'd have to grow fins, or you'd have to have fins. So all right.
So now you've got bubbles that are in the coolant at that point.
Right.
So now the pump is pushing liquid coolant in one side of your module, and it's pushing out a combination of bubbles and coolant out the other side.
Right. Right.
So now your hot column is going to have bubbles, a mix of bubbles and coolant in it. And if your heat exchanger,
and the pressure now the pressure that you're still on that, you're still pulling the same vacuum, so it's
right. So you're below atmospheric at that point.
Right.
So the only thing that's going to make the bubbles go away is to get the bubbles themselves back below the boiling point. Because the bubbles exist because the coolant got above the boiling point.
There's two ways of doing that. You could either bring the temperature of them down, flowing through the heat. So when you flow through the heat,
Well, actually, even flowing through the outlet manifold, because the really hot surface is going to be the heat sink.
correct.
The heat, or the heat exchange portion of it there.
And the liquid is obviously going to be, by definition, the liquid around it will be lower than 65 C, but otherwise it will be boiling.
Right. So
so you'll be cooling it down as it goes up the return pipe. It will be, the bubbles will be being cooled anyway by the liquid around it.
And if the bubbles cool, they'll disappear.
But
because
on the basis of how efficient how efficient is that transfer?
The other thing that you're going to have to be careful of is the design of the module so that the bubbles have a good escape path. So
yes,
the outlet, the coolant outlet of the module may end up wanting to be on the top of the module.
Well, no, that's what I've got. So that's why these modules are vertical. Actually, let me just share my screen. So I just brought this screen up while we were chatting. Here, can you see this?
Yes.
So in fact, if I so this is an early version of the wall that I did, but it showed the guts before I did it into a little brick. So here you can see. Oh, hang on a minute. It doesn't work with a. Anyway, so here you can see these columns. So you can see the pipes at the top. You can see I've put a little Mickey Mouse pump that I just scaled to fit my needs. And at the top is this heat exchanger here. You see that?
But I think the pump is really going to be on the cold side, not the hot side.
Yeah, this is the cold side. So
okay.
This is the cold side feeding down.
Right. So that section of pipe right there, because the pump is pushing against the throttling valves, could be above atmospheric.
Yeah, here it would be. Yeah, it'd be pushing above. Yeah, so it's pushing. Yeah, this pump will be pushing, pressurizing these, and and if you look on the left here, we've got one module populated here, and the rest are not. So you can just sort of see the valves. So in here, this was an old design where I had 2 inlets and 2 outlets. So again, this is ignore the detail here, but you'll see that I've got a valve on both of the inlets. We didn't bother with a valve on the outlets.
Yeah, I think that's still okay.
Okay.
But the only thing you had some pictures that showed details of the module itself.
Yeah. So you mean in terms of
so the the outlet of the coolant is probably going to want to be on the top side of where the coolant cavity is inside of the module.
Yeah, so the orientation of the module is such. In fact, so this design, it was horizontal, and you'll notice that the new design is vertical. So in fact, if I go back to the PowerPoint presentation, keynote file, open this one here. The barrel. Yeah, so this one. I want to show the animation, so come on. Right, here we go. So here's the animations showing, so you'll see the inlet and the outlet are both at the top of the module. And it goes into the manifold first. It's just animate around the board.
So that's the connector side.
That's the
So the,
connected side.
okay, so stop there for a sec.
Yeah, that's the chip side. You want to go back to
Okay,
the side?
so this surface that we're actually looking upwards, right?
We're actually looking, well, no, we're actually looking at, well, it depends on the orientation.
Well, that's the key, I think.
Yeah. So those two power pins on the left are actually on the top of the module. So you rotate this whole thing by 90 degrees clockwise.
About which axes, though? So as those do those pins point toward the back of the power wall?
Yeah, they point towards the power wall because you blind mate the water and the power together.
Okay,
So you're looking at the module from the wall, but you've got to rotate the
okay,
module.
that's fine. So this is in the this is in a normal orientation right now.
No,
So
you need to rotate it by 90 degrees for it to be the vertical. Look at if you're the wall, you're staring at this chip is what
yep,
you're doing.
yep, that's fine.
But rotate
So
it clockwise by 90, and the power pins are at the top, not on the left.
okay, but still the printed circuit board is parallel to the power wall.
Exactly.
Okay, so then where does the coolant more or less come into this chamber that we're looking
it
at
comes
here?
in on the left as the picture shows. You're on the top. So let me continue the animation.
Okay.
Just finish this animation. Different chips. So this now rebuilds the module. So you see it gets put back together. The immersion chamber is now underneath, and the conduction's in the top.
Yep.
And there's a water inlet going into the manifold and outlet on the other side. And then it plugs into the wall. So your inlet's on the left, your outlet's on the right.
Okay. So the only thing that you'd have to be careful of is that there's an easy path for the bubbles that will be inside of that coolant chamber to get to the outlet of the module.
Right. So when me and Ben were doing that, we actually did think about that, and we were looking at where we were trying to get it so that any air bubbles would percolate their way out of the module. That's why we changed the orientation, and we had the inlet going in, and so the inlet comes in and it comes on the manifold, and it then pushes down through the manifold, and then it transfers across to the immersion chamber on the other side. Yep. And then it comes up the immersion chamber, and then it comes back into the manifold and out the hole. Yep. Out the return.
And then you've got a vertical manifold that's collecting the output from all of these modules.
Right, vertical manifold. Well, then, so you're looking at the wall now. So you've got 8 modules high on each one. So so your return pipe goes up through all of those, obviously.
Right. So a given stack of 8 modules has got a vertical coolant in pipe and a vertical coolant out pipe.
Yes. One in, one out. Yeah.
One
and
out.
We've made the in pipe and out pipe 8 times the area of the Staubley area of its interconnect.
So
it's not
the outlet column is going to potentially have a mix of coolant and bubbles in it.
Yes.
And so best case would be the module that's at the bottom. Its bubbles are going to be traveling through coolant that's below the boiling point. And the bottom module's bubbles may never make it to the top of the column.
Well, they may turn back into liquid, you mean?
Right. But the bubbles from the top module aren't going to be traveling through any significant column.
They hit the heat exchanger.
Right. So hopefully that the bubbles inside of the heat exchanger itself would cool sufficiently to disappear. But if you were, that's a little bit of a bet. I'd like to see some simulations or some empirical tests done with that.
Yeah. I guess the efficiency of boiling a hot gas, liquefying. I wonder what that time constant is, so to speak.
Yeah, and I wonder if bubbles in the heat exchanger are actually a detriment to the cooling the coolant.
Its ability to heat exchange. Yeah.
So
Yeah.
that would be an
That'll be
interesting thing.
That'll be a question to ask the suppliers of that, because I'm sure on their warranty, if that
Yep.
wears out more quickly, I'm sure they'll be stating.
Yeah, I don't think the bubbles would damage the heat exchanger, but the pumps don't like it because the pump impeller will actually erode the pump impeller.
Right. Okay. Well, so
Um,
so back to my other presentation, which is, like I said, out of date, but back to this one here. Yeah, so we have the heat exchanger before the pump, and then so what I was thinking is, if we do need this expansion chamber, you'd have the
would most
pump
likely-
with the expansion chamber, and then another pump to then feed the
No, the expansion chamber just acts like a capacitor.
Yes, right, understood.
So if the expansion chamber was on after the heat exchanger and before the circulating pump, then that accumulator, whatever you want to call it, would be an opportunity for the bubbles to separate from the liquid coolant.
So, but if the heat exchanger's done its job, we don't need the expansion chamber then.
True. But that's something that I think experiments would show you.
Oh, so but what, we only need one pump because
Right.
the vacuum's being pulled. No, but you're not going to be able to pull the vacuum unless you've got an expansion chamber of some sort.
Yeah. See, the other thing that I was thinking is that if you had an expansion chamber after the heat exchanger, before the pump, right about where your pointer is now,
right, just up there,
and the vacuum pump is actually connected to that chamber, then if
so it would pump the extra pressure into the chamber, and the chamber would.
No, I'm thinking the chamber is on the low pressure side to keep the bubbles out of the pump. So after the heat exchanger, before the pump.
But then you're not going to be able to pull the vacuum. So I'm thinking that you want to pull a higher pressure. I guess these valves on the inlets are the things that are causing the pressure differential, aren't they?
Correct.
But
so the pumps are pushing against those valves.
Right, but this pump's going to pressurize this leg, depending on if these valves are all of them all but closed. It's going to be putting a hell of a pressure in here, but it's not going to be able to pull a vacuum because it's one complete loop. So you need to be able to have some sort of expansion chamber for a pump to pull even more vacuum if possible. Am I missing?
I don't think the circulator pump has got anything to do with the coolant pressure or vacuum or anything on this. So the coolant pump is taking liquid coolant and pushing it into the supply side column and pushing against the throttling valves. As soon as the coolant goes through the throttling valve, it's in the low pressure side of the cooling system, the below atmospheric side of the cooling system. And if the energy, the TDP on this is low, then you may not get any boiling at all, and your heat exchanger chambers would be liquid. The outlet side, the hot side column, would be still completely liquid. And
so, all right, if this was entirely liquid, let's ignore the evaporation a minute.
Right.
So if this was filled to the brim with water, all the air had been escaped out of all the modules and everything.
Okay. So to start off with, you need a accumulator on this anyway. Otherwise, you'll blow the pipes up.
Right. What do you mean by is that an expansion chamber? Accumulator?
Expansion chamber, right?
Yeah. Right. Okay. So we are on the same.
Because if you were a single phase, completely liquid system.
Right.
And you the system is, your first power up, and all of the coolant in there is at 15 degrees C.
Oh yeah, as it gets hotter, you need the expansion chamber because you take up more room as it expands.
Right. Otherwise, you'll blow the whole thing up.
Right,
So
and as it turns into a gas, even more so. In fact, as it turns into a gas, your pressure is going to go up, isn't it?
Well, that's what you need the vacuum pump for, is to maintain the low pressure side of it.
So this is where so mentally, based on what I've been saying, we've been talking about, I mentally felt there was one pump here.
Yep.
It's pulling the vacuum, and it goes into the expansion chamber afterwards, and then there was another pump pulling it out of the expansion chamber and pressurizing this side. That was my mental picture of this.
Yeah, I don't see how that would work.
Alternatively, one pump and an expansion chamber afterwards, and this area here basically is going to be controlled by these valves. So
right, and that would be above atmospheric.
So gravity and the vacuum is going to be pulling water. So
now the CDUs that we make work just like that. So that we have a accumulator on the output of the pump, and that provides the equivalent of a capacitor in an electrical circuit.
Okay, then so
in this case, the pump would pressurize the accumulator or the expansion tank, whatever you want to call it.
Right.
And once it got up to a certain pressure inside of that manifold there, then the pump would slow down because it doesn't need to do that much work. So now it's put coolant into the expansion tank, and it's sitting there, and now the pump speed throttles back because it doesn't need to circulate that much coolant. So you load software into this.
Your capacitor needs to be big enough that you can successfully pull the vacuum still with low flow rate, I guess.
All right. So if we say single phase for the conversation for a second.
Okay.
So now you load software up into this thing and you start your Bitcoin mining up. Your coolant valves that are on all of your modules are going to open up.
Right.
And probably open relatively rapidly. So the coolant flow rate need is probably going to increase very rapidly.
Right.
And may increase faster than the pump speed can increase, or the pump volume can increase.
Right.
And that's what the expansion tank takes care of.
Right.
So you'd actually pull some coolant out of the expansion tank until the pump can get back up to speed and replenish that. So the pressure that's on the pump side of this and could vary a little bit, but it would be above atmospheric because you're pushing against the throttling valves. On the other side of this,
you know what this yields, because you've opened the valves up full bore when you're still a liquid to keep it cooling, and then suddenly you need it to boil to transfer more heat. Suddenly you have to close the valve down to get the boiling point, or you need even more pump pressure, or you need such a powerful pump that it can pull a vacuum even with all the valves open.
Yeah, and so that's why I don't see the coolant pump. I don't know. On an air conditioning system that works, but those are usually piston or rotary pumps. They're not centrifugal pumps. They're positive displacement pumps.
Right.
And the pumps that you would normally use for a liquid cooling system are not positive displacement. They're usually centrifugal pumps. So that the suction that you get out of a regular coolant pump, I don't think is very high. So if you stuck your thumb over the inlet to the coolant pump on there, I don't think it would pull much of a vacuum on there.
Right. That's
So
we're back to the can you pull a vacuum question.
right. So that's why I was thinking a separate vacuum pump.
So where would that go?
Somewhere between the inlet to the circulating pump and the it could either go on the I don't know which side of the heat exchanger it would want to go on.
Well, if you didn't want to get bubbles in it, I guess it would have to go on the outside on the return side.
And this is why so if you had a separate vacuum pump and the vacuum pump is on the hot side of this loop, then the vacuum pump is just responsible for maintaining the vacuum in there and has nothing to do with the coolant flow. All it's doing is reducing the pressure in there so that the water will boil.
The trouble is, then there's going to be bubbles damaging the impellers of the vacuum pump if you put on.
The vacuum pump shouldn't see any of the coolant. That's one of the keys. So that's why I was thinking that you need a like a separator tank or expansion tank or something like that.
The vacuum pump shouldn't see the coolant. So how does the vacuum pump work then? So I'm completely understanding that.
So on the hot side of this, you would also have an expansion tank.
Right.
And say the liquid level in the expansion tank is halfway up the tank or so.
Yeah.
And so there's vacuum above the tank instead of the normal pressure. So you've got vacuum in the top of the tank that is air, hopefully, and liquid below that. So if the vacuum pump is pulling on the top of this tank, the vacuum pump never sees the coolant. All it sees is vapor.
Okay. So how does the coolant get out of that vacuum space into the heat exchanger?
So the
oh, it's a separate tap off, is it? In
right,
the liquid.
right.
Okay, so it's right. Okay, thank you. I can now picture how it mechanically works. Right. Okay.
So you might actually have like a coolant in, coolant out connection to the tank.
Yes.
And they use the
right. I got you. Yes.
So if you want to buy one, go down to your local race car shop and get a oil tank for a dry sump system for a race car.
Oil tank for a dry sump.
So they do systems like this for oiling systems for like Grand Prix cars. So on Grand Prix cars, you don't want the oil in the pan of the engine because the centrifugal forces move the oil off to the side of the engine.
Oh, yes.
Because you can pull more than a G.
Yes.
So that means all the oil is on the side of the engine and nothing in the bottom of the pan.
Oh my gosh. All right. Yeah.
So the oil pump has nothing to pump. It's pumping vapor, not pumping liquid.
Oh my God.
So what they do is they have a series of what they call scavenger pumps, and these are actually positive displacement pumps that are belt driven off of the engine, and the inlets of these go to the sides of the oil pan, and the oil pan, instead of being 20 centimeters deep, is like 5 centimeters deep because there's no oil in it. So the scavenger pumps pump the oil out of that, and they pump it up to this separator tank. So the separator tank might hold, 8 liters or something like that. And the pipes from the scavenger pumps go into the separator tank, and that's a mixture of air and oil and things, and it goes into the separator tank. The air stays in the tank, the oil goes to the bottom, and then and that's the feed to the pressure pump for the oiling system.
Right. Right.
So this is exactly the same kind of thing, that you've got a mixture of air and coolant coming into the tank, and gravity will keep the coolant toward the bottom, so that the bottom of this goes into the heat exchanger and then into the and actually putting this on between the pump and the heat exchanger might be the best place.
Wow.
Because
So
there'd be less bubbles in it, because the heat exchanger potentially has taken all or most of the bubbles out.
yes, yes.
And then the vacuum pump just pulls a vacuum on this. And as long as the pump is connected to the bottom of the tank, and as long as the pump sees pure liquid, then the pump's probably happy.
So that's why the pump, that's what, and you still need the circulation pump because you got to move the fluid around, right? So,
Right.
all right.
So you
Brilliant.
could end up with, potentially one vacuum pump that is servicing, a whole wall.
Right.
Uh,
Servicing a whole wall.
so you've got several of these separator tanks or expansion tanks on each of the coolant loops, but there's nothing that so I don't see that you would need to have an individual vacuum pump for each of the coolant loops. You could have one larger pump with pipes going to the tops of the separator tank, and all it does is maintains 0.4 or 0.2 or something like that atmosphere.
Okay, I'm missing.
Because all of these loops want to be at the same pressure.
Right, but you'd have to mix all of those loops liquid if you were
No, because you're at the top of the separator tank. You're only dealing with the gas at that point. The liquid stays at the bottom of the tank.
right, appreciated. Okay, well, you'd need separate sections in the tank for the different fluids of the different columns.
Well, I would say a tank per column, but the tops of the tanks could be connected to a vacuum manifold.
Oh, they could be connected to the same vacuum pump.
Right.
Right. I got you now. Okay.
So
Okay.
the only thing the vacuum pump management loop says is, okay, maintain 0.4 or 0.2 or whatever it is atmosphere.
Okay.
So the only thing that I'm not 100% sure of is what the gas in the top of this tank looks like. Is it a fog, or is it cooled enough so that the bubbles went away and it's...
See, my mental picture of this is that, I mean, it's a bit like you said, the immersion tanks that you've already seen with the chips
Yep.
boiling and the bubbles boiling to the
Yep.
top is still 99% liquid, right? It's just
Right.
so I'm assuming, because we're dragging all of the liquid out in an immersion tank.
Yep.
The liquid's just staying there, isn't it? And the bubbles are being collected, whereas we're moving everything around. So if we think of this design, so mentally, I've suddenly realized that these valves are going to be 100% open when we're pulling the full vacuum. Because this will operate as a closed loop liquid solution to begin with. And we will, as the modules get hotter and hotter and hotter, we keep opening the valves and opening the valves and opening the valves until they're fully open. And then we must have the boiling take over to do any more cooling.
Yep. So
otherwise the loop ain't gonna work.
We have an accumulator tank between the heat exchanger and the pump. So there's a couple of liters or something like that of liquid coolant in the bottom of the tank, so that the circulating pump has always got liquid to feed from, and it's pushing liquid down into your cold side supply manifold, and then pushing, even if the throttling valves are all the way open, it's pushing just liquid into the heat exchanger chamber.
Right.
So bubbles form inside of that chamber because our TDP is sky high. But because the pump is pushing liquid into the chamber, the hot liquid and the bubbles only have one way to go, and that's out the outlet of the chamber. And at this point, I don't think so the pressure that's between the pump and the throttling valves could be,
Hang on
like you
that.
said, could be fairly close to 0.2 or 0.4 atmospheres or something like that.
Yeah, actually, what you just said just triggered. If this vacuum chamber is in the hot loop, then the bubbles will be bubbling off into the
But if
vacuum area.
if this tank is after the heat exchanger and
Right.
before the
Okay.
pump,
Okay.
then
Okay.
then the
Then it's
coolant
gonna be liquid. Right. Right.
then the coolant is going to be back to a reasonable temperature.
Correct.
And I would expect that the majority of the bubbles would be gone by then.
Correct.
But if there are bubbles, you don't want the bubbles to go into the pump because it's tough on the impellers. So the bubbles would go up, would burst on the surface of the coolant that's in there and then go up into the upper half of the tank and be
Right.
separated from the coolant.
So when we pull this vacuum, the entirety of the entire liquid in the pump in all areas is at that vacuum.
Depending on your TDP. If your TDP is really high, then I would say that's correct because there'd be no back pressure in the cold side of the loop. If the TDP is low, then it's quite possible that the throttling valves being closed and the circulating
We'll
pump
give you a
being
differential in that vacuum.
right.
Right.
And so the cold side of this at low TDP could go above atmospheric.
The cold side would go above. Correct. Right. I got you because our valves are all closed now because we're not getting
Right.
enough TDP.
Right.
Oh, but guess what? So it does work. Because
Right.
if we close those valves, we've got high pressure on that on the cold side, but you're still pulling the vacuum on the other side, so you're probably still going to get boiling.
Yep.
Even though even though you're only burning 200 watts, not a kilowatt, you could still boil because you're pulling the pressure, and if the die is at 85C, you would still boil on the surface.
Yep. But what you may end up finding is that if the heat exchanger surface area is large, that the energy absorption capability of the liquid water is high enough to absorb all of the TDP, and it doesn't boil. Or if it boils, the bubbles don't last very long inside of that chamber. They may go instantly go back to a liquid.
Right.
So,
right. Yeah, because it's so cold, because the liquid is so cold, relatively speaking. Although you're getting that boiling, you're instantly dissolving back into the liquid, the volume of liquid.
Right. So right at the exchanger surface, there might be some bubbles there.
Right.
But they might never make it out of the chamber.
Right. Agreed.
All right. This would be really interesting to do with.
By the way, I just looked up your company. You're freaking huge.
Yeah.
You're part of Raychem.
So no, we own Raychem.
Oh, you own Raychem.
we bought Raychem from AMP.
Because I'm looking at nVent Raychem. It's looking at all.
Yeah, that's actually not one of our larger divisions.
So it looks like you do. It sounds like you might be involved in all the HVAC systems and industrial heating systems and everything.
Well, we've been doing liquid cooling systems for more than a decade. And
Oh, so relatively speaking, you're a new company. You're a young company then.
well, the oldest piece of the company is from the 1800s.
But is that an acquisition or
Yes, that was an acquisition. So
so this was set up as some private equity and then just vacuumed up a whole bunch of old
well,
ones?
so it started with a company called Pentair,
Oh
which
yeah, I know
was,
Pentair. I use the pool system.
yes. So
I've been cursing their chemical stuff. I'm a genius of the chemical because I've got all the automatic dispensers.
uh-huh.
So I'm a genius of that shitty piece of software that runs on that Pentair control software.
So so I started with Schroff, which was
Okay.
a German company,
Yeah.
uh, building VME
I was
chassis
going to say
and
they're the enclosure. They're the
right, right. That's where I started.
right.
And Schroff started in the early 1960s doing modular power supplies and things like that. In 94, Schroff got bought by Pentair.
Okay.
A couple of years before, Pentair had bought Hoffman Engineering, which is like a Schroff, but on the industrial side and instead of the electronics side.
Right.
So if you want a 19-inch cabinet that you can leave outdoors and shoot at with a shotgun, then Hoffman makes cabinets like that right in the catalog. And so over from the early 60s up until the 90s, Pentair went through a lot of gyrations as to what company they were. And they've had a very, very long history of buying underperforming companies, improving their management, and then dramatically increasing the value of the company and oftentimes selling the company and going off and buying something else.
Okay.
So they did a lot of that over, let's see, from 94 till when did, so in the less than 10 years ago, Pentair had quite a number of companies that they had bought that were in the electronics field. So the thermal side of it, which is all the tank heaters and things like that, that we bought from Tyco,
Right.
and Schroff and Hoffman, and another company called Erico, which does like grounding systems for data centers. So before you pour the concrete for the floor, a lot of times the data centers will have a giant copper mesh inside of the concrete floor. That's the grounding reference system for all of the cabinets and all of the equipment.
Yeah.
And they also make raceways for all the conduits and ducting that goes up on the top of the data center for the coolant and power and data and things like that. They make all of that sort of stuff. So Pentair had built this electronics group that was a number of different companies that were in related fields. And then Pentair decided to get out of the electronics business and stay mostly in the pumps business. So they spun off the whole electronics division, and that's what nVent is we're a spin-off of Pentair.
Oh, okay.
So we're a separate company now. So I owned Pentair stock, and they did a 2-for-1. So I got a share of new Pentair and a share of nVent after the split.
Okay.
And so I still own Pentair stock. So thank you for buying a pump.
Yeah.
So now we have this company that's primarily electronics related. So we do a lot of the
It's
infrastructure.
electronics related, but it's more it's not electronic. It's related to the electronics industry, but it's infrastructure stuff.
Right. It's almost all infrastructure related. So it's the physical housing of everything. power distribution, cooling.
Oh, well, so you're going to be interested in building the walls and designing getting rid of those 19-inch racks for me.
Yeah, my job within the company, I'm actually retired and have been for a couple of years, but I take care. I'm the standards rep for the company.
Okay.
So I go to VITA, PICMIG, OCP, ANSI, IEC, IEEE meetings and things like that to see where the standards are going and if there's business for us in developing standards and to try to influence the standards to use technology that we're capable of making.
Interesting.
So I saw thermal management, and that's one of the things that we do, and decided to keep an eye on what you're up to. And I think this is interesting technology. I don't know whether our company will be interested in participating or not. That's not my decision. So all I'm doing is reporting on the technology and trying to help you a bit.
Great. Thank you very
so
much. You've been tremendously helpful on the few calls you joined us on. So fantastic.
So we have a lot of the bits and pieces for this. The modules themselves, I don't think so. The inlet manifolds and outlet manifolds we already make for cabinets. They're welded stainless steel assemblies.
Right.
We do inline heat exchangers, back of the cabinet heat exchangers. We're dabbling in immersion cooling. We do CDUs that are relatively large. A single CDU that's over a megawatt.
Right.
So we do some very large scale liquid cooling. So this is interesting, and it's very close to the kinds of products that we make.
So do you think, I'm going to have to run because I've got another meeting coming up, but do you think that, I mean, if we could get money from the government on this, that your company would be interested in
I don't know. Not my call. All I do is report on this, and if you're interested in soliciting the company for participation, then I can put that into my report from today, and I'll find out who would be the best contact for you within our company.
Right.
And then
because this infrastructure piece is, I mean, the bigger picture of, you get the bigger picture of where this can go, and I'm just looking at companies.
Well, I mean, this could be massive business.
It could be. I mean, but obviously, it's like everything. All these commercial companies just aren't interested because, well, is Facebook asking for it? Is Microsoft asking for it? No, they're not. but they might be if we could do a good job of this. In fact, you could own the entire freaking infrastructure industry if they did, sort of thing.
It would be. There's a lot of questions still as to how this would work and how you would make it.
Of course, I mean that's that's the problem, right?
But I think that you could do a simulation of this on a somewhat smaller scale. And if you built one of your chambers there with an electric heater on the back side of the printed circuit board so that you could vary the TDP that's going into it.
I mean, that's the test vehicle we were talking about earlier, yeah.
Right. And then have a Lexan sheet enclosing the chamber so you can actually see what's going on inside of the chamber. And potentially plastic or glass tubing for the in the manifolds. You can actually buy clear plastic plumbing pieces for liquid cooling systems. And a lot of our systems actually have them so you can see if there's bubbles in the system. So if you had them on the cold side and the warm side, then you'd be able to see if there's, the pump is causing bubbles, or so you could sprinkle these little clear pieces of plumbing around inside of the system to so that you could see the magnitude of the bubbles under varying TDPs, and so you could mock up one of these walls, not terribly difficult, and play with it and see what it does. It would be really, really interesting to see, after the heat exchanger, if there's any significant amount of bubbles left in the coolant.
No, this has been hugely useful for me, so thank you very much. You've completed the mental picture of how do we pull the vacuum that I didn't understand at all. So what you said, I fully understand now how you would pull the vacuum and why that would work, and you need a separate circulation pump and how that would work. So thank you for your persistence in getting me to understand. And I mean, I'm hugely encouraged by it. I guess it's just, my only concern is the magnitude of these pieces, whether they can be small elements or I'm just off by a massive scale. Like you've got the model here, and so there's the inlet pipe. I think
as long as whatever orientation you put this part in. Right, so that there is an easy path for any bubbles that would be in the coolant to go through the outlet and get into the manifold without making a pocket of bubbles someplace.
Yeah, so that's right. So basically, the bubbles accumulate up here. They do have to make their way out here. So we've got sort of a design here so that everything can sort of collect and go through here up into this manifold, and then there's a path here to this outlet. So this is an area where we could get some trapped gases at the top, I guess. But again, if we design it carefully, and then it returns here into this and then goes through. So all of that, everything I just said, is all sort of horizontal in this. So you as long as the holes were at the top of the channels, then in theory the bubbles should make their way out.
And prototyping something like this, and even not if you had one of the porous stones from an aquarium inside of water, you could build one of these out of plastic or something like that and put a Lexan sheet over it so you could see inside of it and you could see how the bubbles flow. No,
that's good. All right, I mean, I wish I had we had some money and people to do it. But it's good. The more we do, and we still got a model and understand, the less we're going to get.
But I think you could create a flow diagram more or less for this I think I might do
that. Based on what you said, I might do that, and then I share it next week. Get a little block diagram of it.
And we've got a couple of guys that one that works in Minneapolis and one that works in the Black Forest that have PhDs in cooling. They're very, very bright guys, and they are the guys that run our cooling teams. And if I could get either of them to take a look at the diagram and see, at least
put it to pieces.
it would be interesting to see, whether they think it's feasible or not.
Right. Yeah. All right.
Okay.
Very interesting.
Nice chatting with you. We'll talk to you later.
Yeah. Take care. Much appreciated.